Hello and welcome back to this lecture series on computational foundations of cyber physical systems. So, this week we will be starting with Kalman filters, how they are used for state estimation in cyber physical systems, and several other applications also exist for Kalman filters. So, just to have some recap, what we have here is this was my standard example of cyber physical system examples, right. And so, this was our course organization, right. So, till date we have actually covered all these topics up to week 10, and we have learned about basic control design, how to model the formal methods part on hybrid automata based modeling and reachability analysis. We have learned how to analyze complex nonlinear CPS using Lyapunov stability and barrier functions, how to design optimal controllers using quadratic expressions and stuff like that, and how to actually use neural network based controllers also. So, one important thing that we did not talk about there is, even we speak of optimal controllers like LQR and several other kinds of controllers like model prediction and others. So, they are based on optimization functions, and we have shown how such optimizations can be solved in real time. But in many cases we also assume that the full state of the system is known to the controller, but it is unrealistic. So, it is also possible in many cases that the full state is not known. What you have access to is just a set of measurements about the system. So, this is precisely where you need to understand that from such measurements how one can actually estimate the state, and this is where the role of observers or predictors and estimators will come in. And Kalman filter, as it happens, is one such widely used state estimator. So, this was invented by Professor Rudy Kalman long back, and it has till date it has found widespread application into domains of control and several other interesting electrical engineering discipline oriented domains. And so, we are just trying to give you a mathematical derivation of Kalman filter here, and we are just trying to show you how it is to be put in practice. Let us remember that this is a quite involved topic. There are a lot of deep mathematics and complex foundations of this topic, but we are just taking a simple linear algebra approach, and we are trying to figure out how the basic Kalman filter equation can be derived. So, that it will be our approach here during this coverage. So, it is an optimal estimator in case of assuming Gaussian noises, right, and it is trying to infer parameters of interest from inaccurate noisy observations. Okay. And when we say noisy observations, we are assuming that the noises are Gaussian, okay, and it will minimize the mean square error of these estimated parameters. Due to such Gaussian modeled noises, whatever is the error coming out in a mean square form, that an expression will be created, and we will try to figure out what is the exact filter which minimizes that expression. So, that is the basic approach here. So, in general, how is state estimated and how are such state estimates put into practice? So, typically that is how the control works. So, suppose let us assume that you have indeed designed such a Kalman gain or a Kalman estimator, okay, and your original controller is having some gain k. Okay. So, typically this is how you put it into practice. You will have the open loop plant. So, this is your plant. You can see that this is in the form of Ax plus Bu, right. Xk plus 1, the update is happening based on Bu plus Ax here, right, and you are getting the measurement y equal to Cx, and this measurement comes to your Kalman gain, right, and so this is part of the observer circuit here, and what it is, this circuit is entirely working on the estimates of the system, like you can see. So, if this is the estimate xk plus 1 based on the previous estimate, then what we can write is xk plus 1 hat is equal to A xk hat plus B uk. Okay. So, xk plus xk hat plus B uk plus L multiplied by this difference, that is the error between yk and the measurement estimate that the observer can generate. Okay. So, L yk minus yk hat minus yk, where this uk that we have, what really is it? So, this UK is in this case UK happens to be nothing but this controller gain k times the reference R minus x this estimate of x here. Okay. In case your reference is 0 in this place for the controller, so, it is simply our standard equational form, that is minus k x k, but instead of minus k x k you are having minus k x k hat. So, that is the more practical scenario, because we can't expect my controller, like I was saying, that it is going to have access to x k, right. So, for all practical purpose, this controller will have access to x k hat, and this observer is the system which is responsible to generate these estimates x k hat recursively in each step based on its sampling of the measurement y k. So, this is what you observe, and through this observer this is the estimate you generate, and this observer, as you can see, it is kind of mimicking your original system through the structure of A and B's, right. But along with that, what you have is L, which is the Kalman gain. The entire purpose of this gain is to kind of minimize this difference, right, and it will try to figure out a nice estimate of x, so that based on x k's estimate, if I derive a y k's estimate, the difference between y k hat and y k must be very small. Okay. So, that is how this entire equational setting comes in. So, this is my observer, as you can see, and it is generating x k hat, and like I said, for all practical purpose, this is x k hat is what the controller will take as input, because it will ideally not have access to the x k's. Okay. So, we will have some assumptions here, like you will have noises disturbing the system. For example, for the measurements, you see y k equal to c x k, you are adding some noise here E k, right. So, this E k is a measurement noise, and similarly, if you see, this is your evolution equation of the state, and for this evolution of x k, you have also added one noise term, that is V k. So, that is your process noise. So, you are considering this V and E, the process and measurement noise, as discrete time Gaussian white noise processes who have some 0 mean, and their variances are like this. So, you have the variances and covariances given by these terms. So, variance of process noise is R 1, variance of measurement noise is R 2, and their mutual covariance is R 1 2. Also, you will have the initial state of the system x naught assumed to be Gaussian distributed with some mean m 0 and a covariance value R 0. Okay. So, overall, from this picture of actual deployment, that how the system is really going to work with an observer that is generating these estimates, I can write this update equation, right, because you see this is how I am able to generate x k plus 1's estimate using a x k hat b u k, and I am expecting the Kalman gain to do a good job, so that it does try to minimize this difference. So, whatever is this difference between its measurement, that is a sampling, and the measurement that it estimated based on previous measurements. So, this residue value, I am trying to think that, well, it is doing a good job, so that this measurement error is as small as possible here. Okay. So, based on this, we can write this update equation like I said. So, this notation, let me explain. So, what this means is that, well, based on the kth step measurement, we are trying to estimate x in the k plus 1th step, and it can be written through these equations, where I can derive this using the previous estimate of k x in the kth step, which was generated using measurements that were observed in the k minus 1th step, right. So, that is how I write this equation, and now what do I have? I have two sets of equations, right, because I have this equation which is trying to kind of model the evolution of the state estimate, and as you can see, this idea of Kalman filter gain is coming as a multiplication factor or the gain corresponding to the residual, because this is my original measurement and this is my estimated measurement, and that gives me the residual, and I am using this to be to be handled by the filter here, and the rest of the dynamics is here, or that was there originally, and with this I am generating the estimate, right. So, this estimate and my original state, if I just subtract from the original state the estimate, what I can write is a reconstruction error, right. So, let x tilde denote the reconstruction error. So, essentially I can write something like this, right. I mean, well, how it comes is very simple. Okay, let me just correct the orientation of the writing here. So, if I just apply the first equation for the state update, and then I have this equation here. Okay. So, with these two, so as we were discussing, let us look at the situation that, well, how I can really construct the reconstruction error here. So, we already have these equations of the next state with respect to the system model, as well as using the estimate with respect to the estimator, right. So, let us proceed from there. So, this is the reconstruction error, which is minus the estimate. Now, if we try to do this math here, so we will reproduce the original state update equation. Here goes the process noise. Now, we will replace this estimate by the update equation of the estimator. We are for the time being so reproducing this thing here. And the estimate of the previous step goes in here. So, that is pretty much it. So, this is the residue which gets multiplied by this Kalman gain, which we are supposed to design. So, if you now simplify this equation, let us see what we get. So, of course, these two will get cancelled out and this 2 gets combined in here and you are left with the Kalman gain multiplied by the residue term. So, now you see if this is your reconstruction error in the k plus 1th step, then the reconstruction error in the kth step is this, right. So, we are doing something like so this is same and the process noise remains, and as you can see we have added a term LK CXK and here and again subtracted it to create this form here. So, that now if you see this is again kind of the reconstruction error. So, I can write this thing, I can write this entire dynamics of the reconstruction like this. So, that is the intention, okay, for why I am writing it in that way. So, this is how this derivation comes, right. So, as you can see this is what we have here, right, A x k tilde plus v k minus L k y minus this c k here. This is the x actually. So, if you recall, this is nothing but my measurement noise here, right. So, that is how we defined the measurement noise. So, that is why we can start writing it like this through the E k, and then if I write it in a suitable matrix form, I can write it like this, right, x k plus 1 tilde equal to I, the identity matrix, minus L k. In a vector form I have A and C in terms of so x k plus 1 is getting expressed in a dynamical equation using x k with the additive term of the two noise values, right. So, that is like a nice matrix vector representation of the dynamics of the reconstruction here. So, this is what we intended to do here all the time. So, that is the derivation and that is how it is happening. So, just to recall, yeah, this is where we had E k being defined, right. So, fine, just recall that this is, yeah. Now, if we just go forward, so let us understand what we are really trying to do. So, I mean we have set up a template equation here, right, an equation which is which is set up with the objective that it will give me an estimate of x based on some previous estimate, and the estimate should be defined in such a way that it minimizes the error between the estimate and the original value, right. So, the idea is that we will define an objective function which will minimize this estimation error here, and the condition of the minimization should be such that that will give me this gain value L. Okay. So, that is how the Kalman filter is indeed defined here. So, this is my objective, then I want to minimize the variance of the estimation error, right, because it is an error, right, it can be positive or negative. So, in the long run I want to do a least square minimization. So, I am going to minimize the variance of this estimation error, which is x k tilde, right. I hope the objective is clear. So, just to recall that I am trying to minimize this value absolute magnitude. Now, this can be positive or negative. So, just like the standard technique we have in combinatorial optimization, we will try to do a least square minimization here. In effect, that means I am going to minimize the variance of the estimation error, right. So, the formula for variance, as we all know, is the estimation of this expectation over this difference, right, of this value of the variable minus the mean multiplied by these things transpose, right. So, basically that is how we are going to always write an square term when we are doing it over a matrix. So, in this way we define this p k, right. I mean we are trying to minimize p k here at the kth step, and the definition of p k is the variance of the estimation error, and this is the standard formula for variance. Now, the mean value of x, if I try to obtain it, so we can check out the equation. So, if you take this equation and if you take the expectation on both sides, then well, this is what you are going to get, right. From this equation, take expectation of both sides, E of x k plus 1 tilde should be well, these are all constant a minus L k c multiplied then expectation of x k tilde, and since the expectation will also be of this and this, and they are all 0 because these are V k and E k are all thus as per our definition, these are all 0 mean Gaussian noises, right. So, in that way this is what we get. Now, observe one thing, we assume that the initial state x 0 that we have here, the initial state x 0 is Gaussian distributed and it has a mean m naught, right. Now, given this x k, let us see how is x k evolving. So, the way x k is evolving is that it is a linear transformation over a series x k minus 1, x k minus 2 like that, right. So, that would really mean this reconstruction error x k tilde, right. I mean since the initial value is Gaussian distributed, and we are essentially doing linear transformations over this multiple sequence of linear transformations over this initial value which is Gaussian distributed, we would expect that this reconstruction error's mean should be 0, right. I mean this reconstruction error will have a 0 mean, right. So, that is why you can always write this thing, that expectation once you are going to take it over x k tilde, that is 0, right. So, this term will become 0. I can always write this as 0 because of this Gaussian property followed by linear transformations. I mean physically speaking, if you think the error will be positive and negative around a 0 mean value, and that is how this is getting set to 0. So, then all that will remain is you want to figure out this thing, what is the expectation of x k tilde transpose. Okay. So, that is the with a 0 mean of this variable, what you are left to do is check the variance, and the variance will be given by expectation of this. So, let us now then go about designing this thing. So, first thing we will do that well, I have to minimize this thing. So, let us first create a dynamical equation of pk. That would be my first step here. So, you see just like we have pk plus pk, I can simply write pk plus 1 something like this, right. Right. So, this would give me so this is the vector form we have already designed for xk tilde, right. And then it is the transpose. So, that would really mean this thing, this same quantity with a transpose. So, or we can just write it down here, a c x k tilde followed by a transpose of this. That means, this row representation would get changed to a column representation, along with that this quantity would have a transpose, right, and the bracket closes. So, this is what we are looking at. So, now so this I and the second term is minus L k. Do not think this is I minus L k, of course. So, essentially you are going to now multiply these terms inside, and that would generate multiple terms here and multiple additive terms. So, if we just write them down, so see you have a quadratic term, right. It has a nice form, some matrix followed by something. So, this would be a scalar quantity and then this original matrix transpose. So, that is a quadratic form. And then at the end you have So, you have got these 4 terms all in a. So, you have 2 of them are in a quadratic form like this, and then you have the other 4 terms, and overall this is getting multiplied by this. So, now what you can do is you can carry the expectation inside, right, because then this expectation will be applied on here, and that would, if you have applied on this A applied on here, then it would generate the term pk, and similarly you see this term, the expectation would be applied here, right, because the others are constants. I mean, these are all 0 means, right, and so this would give you a 0. Similarly, this would also give you a 0, right. You have the expectation of this and the expectation of this that would remain. So then what we can write would be something like this. Right, the expectation is applied here, so you get pk, and then you have things here. So you will have 4 terms when you have a 1 cross 2, and this transpose will give you a 2 cross 1 matrix. So you will in effect have a 2 cross 2 matrix, and the expectation should get inside here, right. So what you will get is something like this. Yeah. So this is the final thing that I get, and of course, if you remember, we have already designated these things, these covariance terms. So this is the variance of Vk, and this is the variance of Ek, and this is the covariance of Vk and Ek, which we have all defined earlier. So this is R1, this was our R2, and these two are our R12s, right. So we can just write this thing as in a nice form, which would be like so. If you just break down these expressions, you will get stuff like this. So essentially, this will be getting multiplied, this will be generating 4 terms, and they are just row wise going to be added, right. So here the first term will be getting added to the first term. This is the first term of the product here, right, and plus R1, right. Similarly, the last term would be Cp, here the term would be Cpk A transpose here, right, plus this is your R12. These are all defined earlier, the covariances, and similarly here and here the this positions term is Cpk C transpose. So this would be your dynamical update expression for pk here, right. So fine, we have got a dynamical update equation for pk, and looks like it's in a quadratic form, because well, here at the start whatever you have, here you have the same thing in a transposed way, and this is quadratic equation has a specific interesting form which is already known in optimization theory, and we will try to use it up to carry on with our goal of coming up with a solution to this. So looking at this, let me just recreate the equation again on the side. So what you have is pk plus 1 So, this is what you have, and if you see this is a specific form which is like this f x y, a function which looks like so you see this is what you have, like you have a form like this, right, because if you see this and these quantities are transposes of each other, the covariances are I mean, so here you have a transpose, right. So, I mean these are all transposes of each other, so that works out, right. So, we are trying to find a well known form, and we are saying that this dynamic update equation conforms to a well known form, and what it is known is we want to minimize this with respect to u here, this form, right, just like we want to minimize this variance of the error with respect to Lk. We are trying to identify what is the gain such that this error variance is minimum, right. That's what is our target here. Now, what is known from this mathematical optimization theory is that if I am trying to minimize this form f x y with respect to this variable u, I mean if there exists some m, such that I can write this q u, this thing, as multiplied by I mean q u times m to be equal to q u times m to be equal to q x u transpose. If I can write something like this, then the form of this function becomes, so this is not y, this is u, of course, there is no y here in this function, then well, f x u So, what we are really saying here is that this dynamic equation is of this form, and we are trying to minimize this thing with respect to this u, okay. And if I am applying the completion of squares technique, then under the situation that this kind of an m exists, like if I multiply x u by m, I am getting this term. If that happens, then I can simply write this up in this form. So, you see that can happen, right. So, you will just need to replace this with this form, and if you simplify, something like this would come, right. So, this comes, and now if you see this is a special form, and we will be trying to figure out that under this assumption that if the m exists, what is the value of u, so that this form is minimized. Because then if we can cast the same problem here, because it is of the same structure, we can also find out what is the value of L, so that p k plus 1 is minimized. Okay. So, fine, we will end this lecture right here, and in the next week we will start from here. Thanks for your attention.